Yeah. Okay.
Is it working?
Yeah. I hope the.
But
No, I
change.
able to cheat.
I don't know if
No,
it
it
will
changes.
change.
Changes.
That you do. Yes. Yeah. Oh yeah.
Oh, okay.
Yes. It's a bit slow, but it works.
No, because it is being transmitted from here. That's why it is slow in here.
Thank you.
Okay, then let's start. Hello everyone, welcome back to Wednesday seminars. Today we have an in-person speaker, Pranav Kukreti. So he is a postdoc at University of Heidelberg. He is working on AGN feedback and his role in galaxy evolution with a focus on the jet-driven feedback from radio-AGN. He did his PhD from Astronomie and University of Groningen in Netherlands 2023 and his master's and bachelor's from ISR Mohali in India. So welcome Pranav. We are good. We are happy to have you here, and you can begin.
Thank you. Okay. Well, good afternoon, everybody, and thank you for coming. So, as you just heard, I'm Pranav Kukreti. I'm a postdoc at Heidelberg University, and I work on AGN feedback in the broadest terms, but focusing more on radio-AGN and jet-driven feedback on the host galaxy. Right, and I work with these people, so you might recognize some names, of course. High size, also here. Project will also be here, actually. Bruno, who was also a PhD student here until last year. Yeah. So before I get into the science of it, just to show you where I'm from these days, this is Heidelberg. It's a small city in the south of Germany. Right, and this is a map, and we have a lot of astronomy institutes. So there are 4 broad institutions of astronomy in Heidelberg. This is Astronomy Institute, which is where I work. The Theoretical Astrophysics Institute, Max Planck Institute for Astronomy, and the State Observatory of Baden-Württemberg. So these 3 are university institutes, and this is a separate private institute. And so any topic you work on, we probably have a good number of people working on the same topic in Heidelberg. So if you're interested, do try to pass by and drop a text if you come. Right. So to start with, I would like to give you some context on what AGN are and what I mean when I say some galaxies have an AGN. So we know that massive galaxies, almost all massive galaxies, host supermassive black holes at their center. We find through observations that in a fraction of these massive galaxies, the supermassive black hole is accreting matter actively, which is and it emits a lot of energy in this process. And this is what we call an AGN phase in a galaxy. Yeah. So give you some notes on AGN. It's a very high energy phenomenon. It has energies being produced here on really sub-parsec scales from the center of the galaxy. But in many cases, it can even outshine the entire stellar light of the galaxy. So the scales at which this is happening is very small, but it's very energetic. Here you see an example of what a normal galaxy would look like in the optical in the nearby universe. And if it has an active black hole at the center, in some cases you see such bright blinding light. When you look at the galaxy, this is a quasar, and you're really staring down the ionization cone of the quasar. This is a very famous AGN NGC 1068. The viewing angle of this AGN is slightly different, and I'll show that in a second. So that's what makes it not so brightly. Right. We are interested in AGN because they are crucial to explain the massive galaxy population, because this huge amount of energy that is released from this phenomenon can couple with the host galaxy's gas and quench star formation eventually. At least that's what we expect it to do. But one thing, before I get into all of this, I would like to note is that an AGN is an event in a galaxy's lifetime. It is not a distinct object or a separate galaxy. It's a phase of a galaxy's life. So it lasts for a very small fraction in a galaxy's life, and it's a transient phenomenon. Okay. It's slow. I will probably just load everything. So right. So this is a schematic of the very broad components of an AGN. Right. You have the supermassive black hole here in the center. You have an accretion disk of highly ionized gas plasma rotating around, and this emits in the optical, in the UV. You have these clouds, highly dense, very high density clouds above and below the accretion disk. These are called broad line emission clouds. They have strong emission lines. They're moving really fast around the black hole. You have a dusty torus that is on larger scales. In reality, we don't know if this is a torus. We know there's dust around the accretion disk. There's still no debate is not settled yet whether it's really a torus geometry or it looks something more inhomogeneous. But we have dust around the accretion disk which absorbs the light if you view it from this side. So if you're viewing something from edge on, essentially in this schematic, the dust would absorb the light from the quasar coming from the central regions, and you would only see this outskirts of the AGN. In the outskirts, you have narrow line region clouds, which are less moving at lower speeds and have lower ionization levels. And then you have, in some cases, a strong jet, which is a jet of relativistic plasma that has been launched from scales very close to the black hole in polar opposite directions. And this is shown here with the yellow thing. Right. So if you're looking if your viewing angle for an AGN is from the top, you would see something like what we call a type 1 AGN, which is what this blinding thing is. You are really staring down the ionization cone. So the AGN radiation is emitted like this way. And you're really staring down this ionization cone. So it really saturates your detector. If you're looking edge on, the dust acts like a natural coronagraph. It blocks the quasar, and you would really be able to see more of the extended emission lines here. Right. Okay. It's this phenomenon of an AGN emits over the entire electromagnetic spectrum. Here is a model spectrum of an AGN where you can see some of the different components. We're going from really infrared, far infrared to X-rays here. And you can see how the different components just pop up at different wavelength ranges. The torus, which is dusty, absorbs UV photons and emits it in the infrared, in the mid-infrared. The optical is AGN disk, the accretion disk, if you can see it, or the emission lines. You have X-rays, which is really tracing the small-scale corona around the black hole in some cases. And yeah, depending on what wavelength you look at, you see different kinds of structure, as you can see in the top panel. So this is to give you a broad overview of the AGN phenomenon. But what I do is look at these things mostly in the radio. And why I do that is because if you look, there are, let's say an AGN in the optical. So this is an HST wide field camera image of Hercules A, so very popular AGN in the nearby universe. If you look at it in the optical, you see a blob like a typical nearby elliptical galaxy, and you're covering this wavelength range. But if you go to the radio side, you see really bright jets that you would miss out in any other frequency. And you see these really collimated jet structure being emitted from the galaxy in opposite directions, and it turns into something more diffuse and extended about a few hundred kiloparsec away from the galaxy. So these jets are emitting in the radio frequencies, and the main process responsible for this emission is synchrotron emission, which basically means there's a plasma of charged particles moving at relativistic speeds, and the magnetic field that is generated by this plasma itself means that these plasma particles are accelerated in the magnetic field, and that leads to synchrotron emission. That's the main process for radio emission on these large scales. Okay, right. When you look at AGN in the radio, it looks really super interesting. There's a whole zoo of radio AGN, this whole variety, and I won't go into the individual processes that do this, make these kind of structures, but you can see, like, you can have really bright jets, that are launched from the black hole and then terminate in a very bright, what we call hotspot at the end. Here, you can have some really wiggly structures going like this, that brighter, closer to the galaxy, but then they fade away farther from the galaxy. You can have two jets that are moving, like a we call a wide angle tail galaxy. So you see this kind of two jets moving in the same direction. And you have, a whole bunch of different morphology. And this is one of my favorite radio galaxies, the Centaurus A. It's bigger than the size of the moon, right? But it's in the radio, so you don't see it this when you see it with your eyes. But it's really a spectacular galaxy. Right. So why do we care about AGN or radio-AGN or any AGN for that matter? Is because you now know from a few decades of cosmological simulations that if you want to reproduce the nearby massive galaxy population, you need AGN feedback to quench these galaxies at some point and keep the star formation rates low enough. So without this kind of quenching, you would have galaxies that are way too massive, way too huge. So on the left, you see a plot of stellar mass over halo mass for a bunch of, here is in the green is a spherical relationship of halo mass over stellar mass over halo mass as a function of halo mass.
Sorry, just
Essentially,
a minute.
yeah. Oh, I thought it was coming from the room. Yeah. Good?
Yeah. There you go.
Right. So this plot essentially what it's really telling you is the baryon conversion emissions. It tells you that you have at a certain halo mass, the conversion efficiency is really high, but at very high mass and low mass end, the conversion efficiencies of baryons in a halo to stars is very low. To reproduce this from simulations, what we need is AGN feedback at the high mass end. So that brings these simulation curves down to this black curve, which is more in agreement with what we observe. At the low mass end, you need star formation feedback. But at the high mass end, you need AGN. And this example on the right is horizon AGN simulations that show what would happen to a galaxy with and without an AGN. You see that these simulations then produce really massive galaxies that don't exist around us with these kind of structures. If you don't have an AGN, once you have an AGN, you can quench the star formation. Okay, so I hope that has motivated why we care about AGN. But now that we do care about AGN, we realize that it's quite a complicated problem trying to understand the feedback from these systems. AGN feedback is a multi-phase and a multi-scale problem. What I mean by that is you have the black hole and accretion disk, but the radiation that is emitted from this from the AGN interacts with the galaxy and with the with the CGM and the IGM on all scales, and it interacts differently on different scales. So here you have really every step is a factor of 10 increase in physical scale. You can see you go really from the circumnuclear region to the ISM scales on the galaxy, the CGM, and the intracluster medium, and you can have different manifestations of feedback on different scales. You can also have different phases of the gas. You can have atomic gas that is, or the cold molecular gas that is impacted. It has different kinematics when you compare it to warm ionized gas. When you're on the intracluster medium scale, you have this hot ionized gas that permeates the space between galaxies. Right. So we know from just to show you two observational examples actually of what I mean when I say different scales. This is a nearby Seaford galaxy. And you can see when we talk about AGN feedback, in this case, we see biconical outflows of ionized gas. So the AGN is here. In green, you see O3 emission from mules. And in red, you see H alpha emission from mules as well. And if you look at the velocity dispersion and the ionization structure of the gas, you see there is this biconical shape that is being that you can see in the galaxy. And it happens when the energy release is interacting with the gas on the ISM scales. Yes. On much larger scales, on intra-cluster medium scales, we see something very different. The jets that are launched by the galaxy actually create these kind of bubbles in the hot X-ray gas that exists in these clusters. Here you see an example of very classical example of this mode of feedback. You see AGN is here. Blue is the soft X-ray emission from the hot gas in the cluster medium, and red are the radio jets. And you can clearly see that there is a big depression wherever the radio jets are, just because the jets have inflated these bubbles in the hot X-ray medium, and these bubbles are then going to expand in the intracluster medium, mixing the gas and sort of preventing it from eventually cooling down and then getting accreted onto the galaxy and forming stars. So this is actually the, if you think about it, really the only way to efficiently transport energy from the center of the black hole to intracluster medium scales. That's what also makes jets very special. Right. So when I talk about feedback in the talk, what I'm really focusing on is this ISM scales of the galaxy, and I'm really only focusing on the warm ionized gas. So the picture is much more complicated when what we are looking at is just really a small part of this picture because it's the easiest to observe. Right, and we use different kinds of emission lines as you'll see basically. Good. So now that we know AGN feedback and different ways it can manifest in a galaxy and the medium around it, I want to spend some time on why we care about radio-AGN when it comes to feedback studies. We know now for a few years that if you take a large sample of AGN, say this was taken from the SDSS survey, about 24,000 optically selected AGN, you look at the ρ3 profiles, which tells you how the gas kinematics is in the warm ionized phase, and you split these AGN into groups of radioluminosity, right? Once you split them into groups of radioluminosity, you see here that as you go to higher radioluminosities, the profile gets broader and broader on the blue side and on the red side. This is telling you that as you go to higher radioluminosity in a large sample of AGN, the gas seems to be more disturbed. Here on the bottom, you see a plot which is essentially a cumulative distribution of the O3 profile widths. The black curve is the AGN, full AGN sample. Red is sources where you see significant radio emission above a certain luminosity, and blue is where there is almost no radio emission. And you can see a very clear difference that there's a strong correlation between the width of the O3 profile and the presence of radio emission. It is telling you that it's possible that the presence of radio emission has something to do with disturbing the ionized gas in these sources. So that means that to understand feedback fully, we also need to care about what is happening in the radio. The other advantage of studying radio is that, as I mentioned before, the radio emission is synchrotron in nature, which means you can date the emitting particles, which is really a unique property of radio-AGN. So here you see an example of a synchrotron spectrum, flux versus frequency in some units. And you have a standard synchrotron spectrum. But as the emitting particles, they get older, the higher energy particles lose their energy much faster than the lower energy particles. So the rate of energy loss goes as E squared, which means you have at the high frequency end, particles lose their energy much faster. You see a steepening of the radio spectrum, as you see here with radiative losses. So older emitting particles will have a steeper radio spectrum. So if you observe a synchrotron spectrum and you can estimate the magnetic field somehow, you can model the spectrum to determine the age of the emitting particles, which gives you a handle on the age of the radio-AGN itself. And this is really unique because this is so far the only way you can really study AGN ages for a significant number of galaxies. There's no other way to really look at an AGN and say how long has this black hole been switched on for. That makes it possible to then understand feedback not just as a instantaneous thing, but also try to understand feedback as the AGN itself evolves. Right. So a lot of my work is focused on the low frequency array. So before I get into the science results, I just want to spend some time on what this is. The low frequency array is a radio telescope. It's a Dutch project. So it's a radio telescope, as you see here, one of the stations located in Netherlands and most of Northern Europe and Northwestern Europe. It's a radio telescope that works at very low frequencies, between 10 and 240 megahertz. This is really, really low frequency for radio astronomy. It's, as I said, based in the Netherlands and Europe. And what this means is you essentially have a dish that is as big, that has the same angular resolution as a dish of the size of all of this part in Europe. So what we do is called radio interferometry, where we combine these dishes in a way that we mimic a very large dish, which would be physically impossible to build. But what that means is that we have now 6 arcsecond resolution images from really the Dutch array here. And if we use the full array in Europe, we get 0.3 arcsecond resolution. And this is really the first time we can ever do such high resolution imaging at very low frequencies. And that opens up a really different view of the radio universe. The other thing I use quite often is LOFAR 2-meter sky survey. It's a radio survey being done with LOFAR of the entire northern sky. This is a plot of the noise distribution along the field. Right now, the public data release is DR2, which has about 4.5 million sources. DR3, which will cover the entire northern sky, will be released next year. And what you'll have is essentially 150 megahertz low frequency images at 6 arcsecond resolution for the entire northern sky. And this is the largest radio survey ever conducted. 80% of sources that are seen in lots have never been detected before. So if you're using if you really need a radio data point or a radio image of your source, check out lots. Right now, DR2 is public, and by early summer next year, somewhere in the northern hemisphere next year, we'll have DR3 as well. That will be public. Okay, so, and yeah, this is what I meant when I say that we can actually go to really high resolutions now and do things that were not done before. For instance, this is 6 arcsecond image with LOFAR Dutch stations. You go to really high resolution at 0.3 arcseconds, and you can now resolve the structure in these radio-AGN host galaxies at very low frequencies. And because you're at low frequencies, the synchrotron spectrum is naturally brighter, which means you can now detect things that were not seen before. So we are seeing nearby radio galaxies, filaments around radio lobes that we didn't know existed. Okay, it has really also changed our understanding of radio-AGN. Traditionally, from the 80s, when people studied quasars and their radio emission, people found that about 10% of blue quasars in the nearby universe have a radio detection, and they call them radio loud. And they said, well, 10% of quasars are radio loud. Now we know that if we actually use really sensitive data and map all the radio detected nearby galaxies, we find that the abundance of radio-AGN is much, much larger than we thought before. Here you see a fraction of radio-AGN as a function of stellar mass in the nearby universe. There's a clear trend of increasing fraction of radio-AGN with stellar mass. And that's not new, that we have known for a while. But what is interesting is that if you go up along these curves, you're going to lower and lower radioluminosities. That means you're picking up really low luminosity radio-AGN. Once you do that, you find that in the most massive galaxies in the nearby universe, the fraction of radio-AGN approaches 1. What that's telling you is that in the nearby universe, almost all massive galaxies have some level of radio emission from an AGN. And that you can only do because now we are going to 10 to the power 21 watts per hour. Now, if you're not a radio astronomer, this number means nothing to you. But this is almost 1,000 times lower than what people traditionally consider radio loud sources, right? So you're able to pick up radio-AGN at really low luminosities. And that is really changing up the picture of radio-AGN, which means we have to also now pay more attention on understanding feedback from these kind of sources, because they are much more abundant. I will skip over this, but essentially this is just telling you, how people used to think of radio-AGN population as radio quiet and radio loud. And people thought that, oh, something is radio loud, it probably has a jet. Something is radio quiet, it probably doesn't have radio emission from the AGN, maybe from some star formation. But with lots, if you, again, decompose the radio emission to star formation and AGN on the y-axis, you see that a lot of radio quiet sources also have high amounts of emission coming from the AGN. So this is also an interesting result from lots. Right, so as I said, the radio-AGN, the importance or the unique property of a radio-AGN is that we can now trace the AGN life cycle, because we can trace the aging of synchrotron spectrum. And what that means is that over now decades of morphological and spectral studies, radio spectral studies, we have been able to construct the life cycle of an AGN episode. It's here you see a schematic that shows what we roughly understand. When the AGN starts, you have a young radio galaxy. The jets have just been launched into the ISM. It's small scale jets, they're bright, compact, and then they grow into, eventually they expand, get galaxy scales and beyond, what we call adult radio galaxies. And then at some point, the AGN switches off. The black hole is not accreting anymore actively, and what you see is just this radio emission that left the galaxy a while ago. And these are called remnant radio galaxies, where you see no active core, but you see really low surface brightness radio emission, hundreds of kiloparsec scale. So this is kind of a dead AGN. In some cases, we find that the black hole switches on again, and there's a new phase of activity that has started before the previous phase radio emission has faded away below detection levels. And these are called restarted sources. So this goes from here to here, and then you have the whole cycle again. So roughly, I won't go into the details of every phase, but just to make sense out of the result I want to show, we take a sample of radio-AGN and we broadly split them into two categories. One is a young phase. In this young phase, we identify radio-AGN with a peak in the radio spectrum. We do that because when the jets are young, the synchrotron emission is bright enough and has high enough brightness temperatures that synchrotron self-absorption becomes important, which means when you look at the synchrotron spectrum, there's a peak in the radio spectrum, right? There's a turnover at some frequency. And you can see this, it will make like the resolved maps of the radio spectral index. You can see some regions that we found here in the innermost region of some jets, where you see absorption, which is telling you that there's probably a young phase of activity here. The second group we made was an evolved phase AGN group, which is essentially, we identify sources where there is no peak and there is an optically thin synchrotron spectrum. In a group of AGN, these are relatively older sources, right? Of course, there's also some restarted sources in our sample where we see multiple episodes of jet. So this is what I meant when I said that there's old radio emission, and then we sometimes find that the black hole is switched on again. Here you can see there are three distinct pairs of jets. 1, 2, and when you go with high resolution observations in the center, you see another third pair. Saying that there's been at least 3 episodes of activity in the same galaxy. And we can see this in the radio. So when we make these two groups of peaked and non-peaked sources, skip over this for now, I'll come back to it, should be the other way. Yeah, so when we make two groups of peaked and non-peaked sources, we find that the ionized, both the O3 emission, the ionized gas, is significantly broader in peaked sources than in non-peaked sources. So here is this 2D distribution of the O3 line profile bits, which we get from SDSS. For these sources, we have a sample of about 5,700 radio-AGN up to redshifts of 0.8. And if you look at the two plots here, on the left-hand side, you have a distribution of the peak spectrum sources, the younger ones. Their typical lifetime is 0.1 to 1 million year from synchrotron dating studies. And the non-peak sources, which typically have ages of a few million years to tens and hundreds of million years. On the x-axis is the radioluminosity, which traces roughly the power of the jets. On the y-axis, you have O3 luminosity, which roughly traces the radiative power of the AGN. So if you make a 2D distribution, you can sort of control for these two luminosities that are really important when we think about feedback, because it sort of tells you how strong the AGN is in these sources. Now, if you compare the two, especially at the higher luminosity end, any box in the peak spectrum sources seems to has much higher O3 line widths than any other box at the same luminosity in non-peak sources. And what that is telling you is that when the source is young, when the jets are young, and you have a source of the same luminosity as an evolved source, would actually have much higher O3 limit. It's telling you that the gas is probably more disturbed in a young source than in an evolved source at the same radio and optical luminosities, O3 luminosities. So this means that the strongest impact of these jets is probably confined to the young stages of the galaxy. When the jets are young, they have the strongest impact, the strongest coupling with the surrounding ionized gas. When the jets evolve to larger scales and beyond galaxy scales, the coupling or the impact on the gas is not as strong on average. And we find that young radio-AGN are typically 3 times more likely to host a disturbed ionized gas emission. Right, and this is also something that simulations have been pointing to, although they haven't concluded this yet. But if you look at simulations of jet-ISM interaction, here you have hydrodynamical simulation plots of jet being launched into some density medium, and then how the jet interacts with the ionized gas and emits in the O3. So these three panels are three stages of jet growth. The jet is here in the black contour. You see as you go down, the jet is expanding at different on to larger scales. This is the column density of the medium, but the interesting thing is the O3 flux, the predicted O3 flux from these simulations, and the width of the O3 profile, which is shown here. The redder pixels show broader profiles. And you see that as the jets grow to larger scales, simulations predict that in the central region, the coupling is gone down. Right? They're predicting that the gas is probably moving to larger scales towards the outside, but in the center, there's not strong coupling anymore. Now, this is only a size of 4 kiloparsec by 4 kiloparsec. So it's not huge. It's really covering the central region of a galaxy. So it's hard to compare this with the result we found because our results are for integrated spectrum for a large sample. These are special result cases. But this does make us think that, it's possible that the coupling goes down in the central region and the disturbed gas just moves out to larger scales in the galaxy. We are trying to test this scenario with the GMOS right now. That's the GMOS IFU on Gemini North. We are trying to find evidence of this disturbed gas and how it's local, if it's very localized or if it's being moved to larger distances. So this is a sample of young sources and evolved sources, and we find some evidence that there's no significantly disturbed gas in these evolved sources in the center, but it's still very tentative. This is really a work in progress. We still have to improve these cubes, the spectral quality. But so far, it does look like the disturbed gas cools down by the time the jets have evolved to larger scales. Right. So we did try to look at this from a different angle using MaNGA. The idea is the same. We're trying to see if the jets and the ionized disturbed O3, if it's more confined to the central region or is it expanding onto galaxy scales. So here we selected a sample of about 800 radio-AGN from MaNGA. Now, this is quite a large number if you think of MaNGA as it was a survey of nearby star forming and some passive galaxies, not really meant to look at traditional hosts of radio-AGN. But if you combine MaNGA with LOTS, and first we find roughly 800 radio-AGN, mostly at low radial velocities. 30% of them have O3 detections, and you see something like this. You probably, a lot of people here have seen MaNGA maps. They're IFU maps of the spectra, and you see this is the O3 width. You see in some very clear cases, really high width values in the center and significantly calm gas towards the outside. In the bottom panel, then we construct the radial profiles of these sources. On the x-axis, you have radial distance as in units of effective radius of the galaxies. On the y-axis, here you have O3 profile width, and here you have the O3 profile width, which is normalized by the stellar dust dispersion, just to account as much as possible for any gravitational motion in the galaxy, because essentially what we're looking for is non-gravitational disturbed kind of effects. And we find that for different groups, especially if you look at the black line, which is sources that have both radio and optical AGN, the gas is significantly more disturbed but only in the very central region. This is central 2 to 6 kiloparsec region. For all other source groups, which are just radio-AGNs, optical AGNs, or non-AGN host galaxies, the kinematics is not significantly different. The most difference we find is only in the central region. That is suggesting that this is really the impact of these radio jets is confined to the central few kiloparsec of these galaxies. Okay, so this was the part about low redshift universe and what we are trying to do with local radio-AGN and trying to understand the impact on the host galaxies. But radio-AGN are also interesting for high redshift studies. And the other part that we are working on these days is study of high redshift radio galaxies. To give you some context of why we want to do this, here is a plot of the cosmic star formation rate density as a function of redshift. You probably have seen this before. We know that there is a peak in the cosmic star formation rate density between redshifts 1 and 3, which is what we call a cosmic noon. There's a lot of star formation happening in the universe. And if you look at the same time at the black hole accretion rate density, which is telling you the level of AGN activity in the universe, we find that it actually correlates roughly with the star formation rate density, right? So you have these blue, green, and red curves, which are different ways of estimating the accretion rate density. And we find at the cosmic noon, there's also a peak in the black hole accretion rate density, which is telling you that this epoch is where we probably have maximum AGN feedback. But observations of this epoch have been very challenging because, all the lines that we are interested in, like the O3 or the rest frame optical spectra, is redshifted to near infrared or mid infrared. And at near infrared, you have from the ground, you have caloric absorption, so it becomes hard to detect these emission lines. But of course, as you know now, these kind of studies can be done with the JWST. We can get really clean rest frame optical spectra of galaxies here and try to understand feedback from these sources. But the other interesting thing is that we can now do this with an IFU. So what we could do with an IFU in the low redshift universe, like with GMOS or Keck, the KCWI, we can now do the same kind of studies, but at much higher redshift. So for this as well, high redshift radio galaxies are actually very interesting. That's because in high redshift radio galaxies, if you look at go back to the schematic of an AGN, you're actually looking along this line of sight, right? So you're looking through the dust, which means the quasar is blocked. And that means you can actually study, you're not blinded by the ionization cone, you can study the emission line gas, you can study the stellar host galaxy, the stellar emission from the host galaxy, you can study jets because they have strong jets, and they have quasars, so you can even study quasars. All of this in the same galaxy, right? And this is the only way to, at high redshift, to study all of these phenomena in the same galaxy, trying to understand their interplay. There are also very massive host galaxies and they trace protocluster densities, but that's a separate thing. Right, so we're right now working with this very interesting case of a high redshift radio galaxy called 4C0324. It's at a redshift of 3.5. On the plot you see here is rest frame optical continuum from near spec in the IFU mode. So this covers wavelength of 1.6 to 3.1 micron. In the rest frame, that is what you see in the optical. Background is what we see in the optical image. It's very messy, but this is where the quasar is. Right? This is where the bright quasar is located. In the green contours, you see the radio emission at sub-arc second resolution from VLA at 15 gigahertz. And you can see that there are these two small jets that are emitted along this axis. The jets go up and down, but at this point, there is a very strong deflection of the jet. Jet gets deflected and essentially gets re-brightened and goes down south. So this means that this told us that this is probably a case of very interesting jet-ISM interaction. If you want to understand or want to look at how AGN feedback can impact galaxies at this redshift, this could be an interesting case. We use something called Q3D fit to model the emission lines. If you have IFU data that you want to model the emission lines, but also subtract the quasar PSF before you do it, especially for type 1 quasars, which is very important. I would suggest taking a look at this software. This was developed mainly for NearSpec and GMOS, so please do take a look. And what we can now get is spatially resolved ionized gas kinematics. This was actually work in a group being done by Bruno. I'm sure most of you know who he is. He's been through a very painful process trying to model the O3 gas of these the O3 emission lines from the source. This is a very messy object. There is a lot of gas all over the field of view, and the number of components we need to model the spectra in many cases is up to 6. which is more than I can make sense out of. So this is a very messy system, but we will try to simplify and interpret what we see. So using these O3 lines, then you can model the kinematics of the other lines. And this is what we find. So this plot here shows the H alpha emission, give you an idea of how the ionized gas is distributed. The white contours, which now realize are not really that visible, are here, right? This is the radio emission. And this is the jet and deflection point where the jet goes sharply to the south. You see the huge, like almost a tail of ionized gas, and then this kind of perpendicular structure of the ionized gas this direction. So it's distributed over almost the entire field of view. This is just a comparison of the different data sets, but that's not from now. Right, so if we compare the different emission lines now, we find something really interesting. So now this is an RGB color image using 3 emission line maps. The red map here is the oxygen 1 line, oxygen 16300. It's a low ionization line. It's a very good tracer of shocks. The green line is H alpha that shows you the extent of the ionized gas. Blue line is O3 5007, which you saw before as well. It's a very good line for tracing photoionization. And if you make an RGB image, you see that there is a strong, like an ionization cone, which goes from here, in these 2 directions, which is almost completely blue, telling you that there is a strong photoionization in this axis. There is hints of red emission here, which is oxygen 1 here, and also right after where the jet deflection happens. And this is oxygen 16300. So as I said, it's a tracer of shocks. So it's telling you that there's probably shocks in these regions, which are ionizing the gas here. So to understand the ionization conditions, we sort of create, we create regions around the gas. So before I get into the regions, I'll just show you the full distribution of the ionized gas properties. Here you can have the RGB image. On the right hand side, you have a BPD diagram. It's a diagram of ionization ratios. Essentially, what it does is it takes ionization lines of different potentials, takes a ratio of lines that are very close to each other, and then just depending on where your points lie in this parameter space, you can figure out what is the ionizing source of the gas. So on the top panel, you see O3H beta and N2H alpha. The labels are very small, but trust me, that's the line here. And O3H beta again, but on the bottom panel, you have O1H alpha. And essentially what this does is it lets you separate photoionization and shock ionization. Things that have stronger shocks have stronger low ionization lines. They will move more towards the x-axis here. Things that have stronger photoionization will move up. They'll have higher O3H beta ratios. So you can really separate the ionization conditions. The models that you see here are essentially models that were derived for quasar photoionization and shock ionization. So this model here that you see, the black lines and the dots are photoionization quasar, a dusty quasar photoionization model. And here you see a shock model, which is essentially telling you what the ionization ratios would be for shocks of different velocities. The colors here are different velocities. You go up in velocity, go more towards the x-axis, stronger shocks. Right, so once we take all these points and put them on the map, we see that they're spread all over the PPT diagram, right? So there's probably different ionization sources in this source. If you look at the east to west region, which is where we had hints of red emission, and look at the most disturbed gas in this region, which we call, identify as gas having velocity dispersion greater than 300 kilometers per second. We find that almost all of these points that are in this region lie in the shock ionization rate, right here. Right? This is telling you that there's confirming that there's strong shock ionization as the dominant ionization mechanism that is also disturbing the gas. The gas here is disturbed using shocks. If you go to, this is just a model comparison. If you go to the south, again, where the jet deflection happens, these points, again, you see, lie here, these green points. Here, now the contrast is not so strong, but you can see the green ones here, right? So they lie here. And it's very interesting because these points seem to lie in between the photoionization models and the shock, right here, where the jet is getting deflected. Just telling you there are shocks, there's enough low ionization lines, but there's also some photoionization that is pumping up the O3H beta ratios. So it turns out if you have a shock plus precursor, you can actually explain these ionization ratios. And what I mean when I say there's a precursor is once you have a shock expanding into a supersonic shock expanding into gas medium, the gas that cools down behind the shock front is actually emitting UV and optical continuum radiation. This, if the shock is traveling fast enough, this radiation can then actually overtake the shock and photoionize the gas that exists in front of the shock. So before the shock reaches the new gas region, the radiation from this cooling gas can actually photoionize the gas. So then you see both pumped up photoionization ratios and high shock ratios. And that's what this model grid is tracing. See, it lies in between both of these. And we find that here you actually see both. You see shock and precursor that can explain the ionization ratio in this region. So probably what is happening is once you have strong interaction with the gas clouds here, the shocks also photoionize the gas. Right. So this is the full picture of what we think is happening. I didn't show the plots for photoionization, but here we find that the most disturbed gas along the ionization cone is actually just explained by photoionization. There's no need for shock or precursor models. But if you go to perpendicular region, you have strong shocks, and here you have a shock and precursor. So all the disturbed gas that we see is actually being pushed or being disturbed by different mechanisms, different manifestations of AGN feedback. And that is really interesting because we can actually study as such at the cosmic noon different manifestations of AGN feedback. This is telling, and if you look at, for instance, the amount of energy in the disturbed gas, we find that shock gas and photoionized gas has roughly the same amount of energy. So this tells you from the energy argument that there is enough energy being distributed through shocks in disturbing the gas. And if we want to understand feedback, we also have to pay attention to these low ionization lines that can help us understand a different way in which AGN feedback occurs. Okay, so how much time do I have? Done or?
Yeah, I guess you have 5 minutes.
Okay, then yeah, I think I'm done. Yeah, okay, so I can now summarize. Great, so this is what I wanted to talk about from the work we've been doing in the past few years. Some of the take-home messages I would like to point out are that when we think about AGN feedback, it's good to think of feedback as not a constant phenomenon. It's a transient phenomenon. The way gas is coupled, the way the energy released couples with the gas changes over an AGN's lifetime. It's possible to do this in the radio, and we are clearly seeing evidence of this. The feedback seems to be strongest in the initial phase when the jets are just launched into the galaxy. The gas couples, it couples much more strongly with the gas. But the impact in these stages is only confined to the central few kiloparsec. Once the jets are on larger scales, we don't find significant impact of gas on average. You might find cases depending on how the jet is aligned with the disk of the galaxy or how powerful the jet is. Some cases where you see jets disturbing gas on galaxy scales, but this is more on average for a population of radio-AGN. When we go to cosmic noon, shocks and photoionization, we see can actually have significant impact on the gas. Even if you're looking at a quasar host galaxy, shocks can be important to understand the full scale of impact of the AGN. And finally, another thing that I'm working on these days, and I wanted to mention, because I would like to see more and more discussion on this in AGN studies, is the trying to understand feedback in a cumulative sense. So if you look at an AGN phase, it lasts roughly from a few million years to 100 billion years or so, right? But a galaxy's lifetime is of the order of a gigayear. So when you look at an AGN, it's a very small duration of a galaxy's lifetime. Probably not enough to impact or quench star formation that can occur on much longer time scales. And here you see, for instance, the example of star formation histories, right? You look at star formation histories of redshift 1 galaxies, specific star formation rate as a function of look-back time. Galaxies have all kinds of behavior. They quench, some quench very fast, go down very quickly. Some quench very slow, they quench very slowly like this. Some quench very late here, and some quench very early. So it's a whole different, so like whole large distribution of timescales over which quenching happens. The galaxy lifetime is also very long. So what we need to do really is to understand impact of AGN in a cumulative manner. And I do this, of course, because this we get something we can do in the radio, I think. In the radio, we can see multiple episodes of AGN activity that have occurred over hundreds of million years. Still not giga-year timescale, but we can go up to 300 to 500 million years, which means you can at least go in this part of the parameter space. And this way, if we actually try to understand the feedback from these sources, maybe trying to understand their star formation histories, we can find evidence for cumulative impact, which is what we really need to do. Most of the studies I showed, all the studies I showed before are actually looking for an instantaneous form of feedback, right? But that doesn't mean that if you see ionized gas, star formation is going to get quenched. What we really need to do is look at cumulative impact of feedback. That's something we are trying right now, trying to reconstruct the star formation histories of galaxies like this at redshift of 1. Hopefully next year, if I come back, I'll probably have something to show. Yeah, from this side as well. Okay, thank you for listening, and I'm happy to take any questions.
Thank you, Pranav, for the wonderful talk. Yeah, please.
So, two questions. First, a comment that I think it's very interesting this plot that you showed, because I work with PSM galaxies and galaxy quenching, but mainly from the point of view of galaxies. And it is very difficult to reconcile what I find in galaxy properties with studies from AGN. For example, PSM galaxies, they tend to have higher metallicities, stellar metallicities, than star-forming galaxies. And if they quenched by gas removal, this doesn't work. So, looking at your the galaxy that you showed from the high redshift case, do you have an image of like the continuum stellar of the galaxy?
Yeah, we have an ugly image, yes. This is, so there is some, okay, so this is the rest frame optical continuum. The quasar is here, and we see this kind of tidal tail. This is not real, something we couldn't remove in the data reduction. But this part is real. And we see a very strong optical continuum here and here. But this is really, this was a 4-hour observation with the new spec. And even after that, we had to collapse the whole solar continuum, get like a single kind. So we don't have the spectra.
Yeah.
But we only have this right now.
Yeah,
This is really, really faint. And we find it like, so you can see it's a bit messy. It has something that looks like a tidal tail. But to give you context, there's also like 5 companions in this small region. Of like 20 kiloparsec, we have like 5 companion galaxies. So it's possible that there is interaction.
Yeah, because when I was looking at your results, what it seemed to me is that you are looking at a galaxy emergent, like and a tidal tail, and probably the many lines that you find, like the 6 components, probably some of it is gas that was expelled during the merger or something like that, and that now is being photoionized.
That's possible. Like some of the kinematics that we're tracing is probably coming from this interaction, the result of this interaction. So really what we try to think of is, we don't know how the gas got here, where it came from, but what happens to the gas once the quasar is switched on. That's what we are trying to understand. But the origin of this gas is, I don't know. Really, I don't have an answer for you.
And the second question is, when you look at the local universe, the galaxies where you see radio jet, like even not the strongest one, even like more modest radio jets, what is the morphology of the host?
So most of them are passive galaxies in the nearby universe. There is, I would say a majority of them are passive. There are some star-forming spiral galaxies where you still see radio jets, low luminosity radio jets. But most of them are passive elliptical galaxies.
Yeah, because like when you look at green valley galaxies, the ones that are catching up, they tend to be spirals.
Yeah.
And I have some students working on this, and we do not find any sign that there is something like transforming them into a. It seems that when star formation stops, if things continue as they are now, they will still be spirals like that.
Yeah,
They will come like lenticulars, not ellipticals.
yeah,
So because this case of like difficult to reconcile.
yeah,
Because like the radio jets we see on ellipticals, but galaxies that are quenching now, they appear like disks,
yeah,
not ellipticals. So
yeah. Yeah, that's true. But I mean, I haven't looked at in this, for instance, the plot I showed the beginning, this one. Yeah, here I haven't looked at. I don't think anybody has looked at the morphology of all of these galaxies, right? But they are, yeah, 10 to 10.5 solar mass. So they are likely going to be more. Like at here at 11, you probably have more galaxies. So I don't know. We don't really have much evidence of Green Valley galaxies showing radio emission.
oh no. Yeah, because like
We looked at them.
yeah, because what we are thinking is that the only way to kind of like reconcile is if the agent feedback is smooth, not be something.
Yeah.
No sign.
Yeah. I mean, yeah, that's true. Like, look at a Green Valley or any galaxy, it's not an AGN. There's no way to know it didn't have an AGN, right? It probably had an AGN, you just catch it in off phase.
Yeah, thank you.
Yes, we can have last question because we're running out of time.
No, no, we have more. No. It's okay.
We are running out of.
Sorry, I.
No, just, so, Rogerio can ask, I can ask later.
Please go. Roger and I will talk a lot after this.
Yeah, I was just, I have two questions. I'll ask just one. What, when you look at simulations of these kinds of systems, how many times does the AGN switch on and off throughout its lifetime?
Well, so we have these analytical simulations that are trying to reconstruct what we see in the radio agent population. When we look at this life cycle, we do some statistics and find sources that are young, that are old, that have restarted. We find that if you look at the distribution of ages, there is a lot of short-lived, much more short-lived sources than long-lived sources. That's probably telling you that the agent is switching on and off quickly. But there is still no like one number for our like a study of that can show you the duty cycle of these sources as a function of mass or something. It's still tricky, but roughly what we say is I think we find that 10 to 15% are restarted and about 10% are remnant. But these are really not so large samples.
And what makes them switch on and off?
That's a big question. Yeah.
Okay.
We still don't know. I mean, people who try to, I mean, that's one of the projects that we are trying to work with, that I'm trying to work with here, Rogerio. When people have tried to look at the host galaxies of these restarted, remnant, and active sources, especially in the radio, the host galaxies do not show any significant differences. But they're also looking at integrated properties, right? Whatever changes are happening on the sub-parsec scale, probably in the accretion flow. And that is very hard to determine. Even with the best ALMA observations, you can really do it for very, very few sources.
And that was more from the point of simulation, because I think from the observation,
There is no, I mean, the analytical simulations just switch an AGN on and off, but nobody simulates an AGN in this transient way, really. I mean, people do cosmology probably switch off the AGN. I don't care if it switches off, but they switch on and off for different time scales. But there's no like probably Roger will say that there's no one galaxy where you can take an AGN and see how it is switching on and off depending on how the gas is flowing around it. So yeah, there is no simulation so far. I think of resolved simulations to understand this.
Okay, go on.
It's okay.
I had two questions. One question is related to what Anna asked, like what determines an agent to start its activity? Can we see at the broadline emissions, which traces the dense region around, say, accretion disk as well, and then somehow relate it to density, and then say, okay, this can be a threshold where the AGN can start assuming the gas pressure?
Okay. Yeah, I mean, so we know the densities of broadline region clouds, but when we look at a non-active galaxy, we don't see the broadline region. So it's hard to tell well, what is the density here if there is any gas clouds? So yeah, that is hard. I don't know if that will give us the answer.
The second question was, it's regarding, you mentioned young AGN, intermediate age AGN, and old AGNs. So now when you study star formation, separating their ages, do you see a random distribution of star formation rates, or is there any, say, star formation is more in these galaxies, a specific star formation?
Yeah, so far, their integrated host galaxy properties show no difference, right? And that is interesting in itself. But maybe expected because we know that, for instance, in Seaforts and optical AGNs, there is enhanced star formation in the center, and he reconciled it saying that this gas is fueling stars, is also fueling the AGN. But in these radio AGN, most of the times the accretion rates are so low, you don't need a lot of gas. So probably maybe that's why we don't see it, because we don't need a lot of gas in the first place to ignite these AGN. But so far there is no result that shows any difference. People have not found a difference. We are trying to understand the star formation histories of these restarted sources. That will probably tell us in the last few 100 million years what was the star formation rate, and if that is comparable to, or if that is any different in restarted sources compared to remnant sources.
Yeah, so can you say like we might see the age difference in delayed star formation, right?
Yeah. I mean, that's what I'm hoping to find. In any delays or any correlation on the timescales of the quenching and changes in star formation rate, essentially, and the activity timescales.
So you were asking a question?
Yes, there is this question also, that sometimes you see radio emission that is not necessarily from the center of the galaxy.
Yeah.
So, but in this case that you showed for the higher redshift galaxy, there seems to be a structure of a jet from the nucleus outside. Then I think there is no doubt, but there is always this question that some correlation that people find with the gas. But not necessarily comes from the nucleus. So there is a confusion there.
There is, and but there you can actually be safe if you select bright objects, because you go to, I don't know if I have it, and just in the interest of time, I will. So if you look at that shock production of radio emission, especially, it's more evident in quasars. It's similar to what you see in supernova remnants, for instance. The shocks from supernova can enhance the plasma and give you radio emission. Similarly, the quasar-driven shocks can also produce radio emission. But if you look at roughly the models that are trying to estimate how much radio emission do you expect to see, if you assume similar efficiencies of quasar energy to shocks to radio emission as, say, supernova, you find that a quasar of 10 to the power 42 Hertz per second in PO3, which is like cutoff for quasar luminosity, will be able to produce radio luminosity of 10 to the power 23 watts per Hertz, which is still at the low end. So even quasars at their best conversion efficiency can only produce low radio luminosity stuff. Once you're above that radio luminosity, quasars cannot do it. There has to be collimated jet emission levels.
Yes.
Hi. So I wanted to ask, how feasible is it to distinguish between a truly young source and a restarted AGN? So are there cases that are like really ambiguous, or?
Yeah. I mean, if I think about it, a restarted source also has a young source in its center. So if you see a young AGN, which is just like bright compact jets or peaked emission like this one, here we found lobes on larger scales as well. But in some cases, you just see this, but then there's no way of knowing if this is the first phase of activity in gas. Probably has had multiple phases. There are cases where it's ambiguous, but in some cases, it's very clear that there you can see really distinct episodes of jet activity.
And for my second question, so you showed us the picture before with multiple sources, like clearly multiple sources. And so in my mind, that happens because the AGN cycle happens around the same time scale that it takes for the gas from the previous cycle to fade away or become otherwise too faint for us to see. And my question is, why does that happen? Is it because the cycle is faster than normal? Does the previous gas take longer to get fainter? Or what is happening there?
Right, so it's hard to translate exactly this. Is a very, people do some kind of first order translations of these scales to activity time scales, and then the gaps and all. But what is really determining how long the jets are switched on off for is really the accretion flow near the black hole, which we don't really know. When you see these, you try to do to first order some kind of dynamical time scales to figure out, okay, how old is this, how old is this, how old is this, and then you try to reconstruct the history of the AGN activity. But that is still very not fully reliable. Right? There is consideration because it's the jet material that expands for the first time, clears out a cavity in the medium. Then the second material expands much faster. So it's not like it doesn't go linearly. Right. So it's complicated to do this. But there are studies and people have mostly found ages of the on-off time scale to be between 0.1 to 10 million years. Thank you.
Is there any more questions? Okay, let's thank Pranav. When we will see you next week.
For the short talks.
Short.
Short talks next week. We have an issue that we don't have enough time. We'll probably have to start at 1 p.m. because we need to leave the room at 3, and I've looked around